next thing we're going to do now is find an expression for energy stored in an inductor. And of course, the energy stored in an inductor means the amount of energy stored in the magnetic field within the inductor. So let's start with electric power, because we know power is related to energy. So electric power, and I'm going to call that P electric, is equal to current times potential difference. So if we're finding the power for the inductor, we'll put in the potential difference across the inductor. So current outside of minus L times di dt. So we're just putting in things we know so far. Then we'll just write that down a little bit more nicely. L times I times di by dt. So let's think about what we found right here. This electric power is negative when the current is increasing. So if current increases, di dt is positive and the power is negative. That means that the circuit is losing power because we found the power of that circuit element. It's losing power, but of course we know energy is not really being lost. It has to go somewhere. Where is it going? Well, it's going into the inductor. It is being stored in the inductor. So P electric is negative because energy is being stored in the inductor. So we can write down what the power, the change in energy of the inductor itself is. It has to be the negative of this. So the circuit loses this much energy because this much goes into the inductor. So we'll say that the P of the inductor equals minus P electric. So what the circuit loses goes into the inductor. And we'll remember that power equals energy over time. I suppose change in energy over change in time. So for our inductor, the change in energy is the change in potential energy. So U for potential, L for inductor. The change in energy over the change in time is equal to the minus of what we wrote down up here. So plus L I di dt. So we can use this expression to find us the expression for the potential energy of the inductor. So if we integrate both sides with respect to time, we'll be left with dUL equals plus Li di. Now let's integrate both sides from a zero current to having some final value of current. If there's no current initially, then there's no energy initially. If we come up to some final current, we'll get a final energy of UL. So then we do an integral over current from 0 to some value of current, L times I times di. So let's see, I think I need a little bit more space than I had ready here. The integral of dUL is UL. That's going to be the integral from 0 to I, L times I di. The L comes out front. The integral of I is I squared over 2. It's going to be evaluated at I and 0. Gives us L times I squared over 2. So our final result, let's write this down. Our final result for the potential energy stored in the magnetic field of an inductor is UL equals 1/2 L times I squared. And that's the potential energy stored in the magnetic field of an inductor. This is probably worth a moment's pause to compare to what we had for capacitors. So when we had capacitors, we said that the net potential energy stored in the capacitor was 1/2 times C times delta V squared. So we see there are a lot of similarities between the capacitors and the inductors. So where are we going to go from here? Let's see what we'll find next. When we did our capacitor, we found other ways to write down what the potential energy was by using the expression that C was Q over V. We can do the same idea here. We can write down what L is, and we can find another way to write down what our potential energy is. So let's do that part next. So we can remember that L is equal to mu naught times n squared times A divided by the length. So this is the inductance of a solenoid or a coil of wires. The inductance depends on the number of turns, the area of the solenoid, and the length. Kind of interesting that it only depends on the physical properties of the solenoid. Just like in our capacitor, it only depended on the physical properties of the capacitor itself. That's what the capacitance depended on. So again, another similarity there. So let's plug this in to this equation and see what we get. So UL equals 1/2 times mu naught times n squared times A divided by L times I squared. So let's see, how am I going to write this down? I'm going to write down mu naught times A times n squared times I squared over 2L. Kind of wrote it like this on purpose because I was thinking about what is the magnetic field in a solenoid. So you may or may not remember that the magnetic field of a solenoid is mu naught times n times I divided by L. So here I have n squared times I squared. I'm going to solve this for n squared times I squared and stick it in here. So n times I is going to be b times L divided by mu naught. That squared will be b squared times L squared over mu naught squared. Okay, I'm going to put that in up there. So n squared times I squared is b squared L squared over mu naught squared. This is going to simplify a little bit. This mu naught will cancel with one of these. This L will cancel with one of these. And our result will be, I think I'm going to go to a next sheet of paper. I want to keep this stuff all together. So now our result will be, when we write down our energy stored in the inductor, so UL is the potential energy stored in the magnetic field of the inductor, that's equal to, what do we have? We have 1 over 2 mu naught. Let's get those constants out front. So 2 and mu naught are in the denominator. And then that's multiplied by A times L times B squared. So the energy depends on the size of the inductor and the magnetic field. So what can we do with this? If you look at area times length, that might jump out at you as volume. So just like we did in capacitors, we could write the energy density stored in a magnetic field of an inductor. So, UL over volume would be UL over the area times the length. That's what we'll give a symbol of a lowercase, no, it's a lowercase u, not a mu. Lowercase u, we'll put a b on there for magnetic field. And this is the energy density of a magnetic field. That's just like when we did the energy density of an electric field with capacitors. So same sort of deal. It's the energy over the volume. So U over A times L gives us 1 over 2 mu naught times B squared. Something that's interesting is we solved this for an inductor, but it turns out this is true for any magnetic field. So then, let's see, I think I'm just going to write that down again so it looks nice. Sometimes it's nice to have your equations all in one place. So UL equals 1 over 2 mu naught A times L times B squared. That's the energy. And the energy density is 1 over 2 mu naught times B squared. Then if you were keeping track of your capacitor equations, so this is the inductor. If you were keeping track of capacitor, we had that the energy in our capacitor, I'll even stay with the same color, the energy in the capacitor, UC, was 1/2 times the capacitance times delta V squared, and the energy density stored in an electric field was 1/2 times epsilon naught times E squared. So that takes care of going through energy. Next we'll do a few examples, and then I think that'll be enough for this section.